Okay, so now we want to address the issue of RL circuits. Okay, and RL circuits, imagine we've got a battery and we've got a resistor and we've got an inductor. And let's let the battery have a potential of E naught, epsilon naught. Okay. And one of the things I'm going to do, I'm going to hook a voltmeter over my inductor, and that is going to measure the induced voltage as a function of time. And I'm also going to put an ammeter into the circuit. And so these are going to measure, right, the current I through time and the voltage V across the inductor with time. Okay, that's what these meters are going to do. So what does the RL circuit theory predict, right? Well, at all times, once again, the total voltage from my two components, and remember the voltage across the resistor is going to be IR, and the potential across the inductor we've just proven is going to be equal to negative L di dt, and these are both going to be drops. So Kirchhoff's rule would read this. This is the energy being supplied by the battery, or the potential being supplied by the battery. This is the instantaneous potential across the inductor, and this is the instantaneous potential across the resistor. And your current, let me write it like this, your current is going to be a function of time. Okay? Now, if your current is a function of time, okay, if your current is a function of time, then as your current changes, that will change the induced voltage across the inductor. And that means the voltage across the resistor will also be a function of time. Now, the potential from the battery is set, okay? That's not going to be a function of time, but this will be a function of time, and this is a function of time. So, what do we do with this equation? How do we solve this? This is a differential equation, okay? This is a bona fide differential equation. Multiple techniques. One of the simplest techniques would be the following, okay? And this will give us insight into how the current is going to behave, and therefore the voltage across the inductor and resistor are going to behave as well. So, if I want to solve this for I want to understand what the functionality of t is, or I is as a function of time. So, what I'm going to do is I'm going to leave my derivative term alone. I'm going to get my other terms on the opposite side. So I'm going to say negative L di dt, okay, is equal to, I'm going to write it down like this, negative epsilon naught plus IR. So I'm moving plus IR to this side, and I'm subtracting epsilon naught. But you'll see why I'm doing it this way here in just a moment, because it'll be advantageous to go ahead and multiply through by this negative sign. So I've got L di dt is equal to epsilon naught minus IR. And I can't say that I love this notation because epsilon naught here is the potential of the battery. It is not the permeability permittivity rather of free space. But I don't like using just generic epsilons either, because a generic epsilon for my potential of my battery could get confused for the potential induced potential across the inductor, and I don't like that. So understand that this is the constant potential of the battery, not the permittivity of free space. Okay. Now divide both sides by L, and I'm actually going to move my work over here to preserve space on the screen. And I've got di dt is equal to epsilon naught minus IR over L. Okay? Now, what you can do at this point is factor out an R from the numerator. Okay? You can factor out an R from the numerator, and then what happens is if I move this term, or really this factor, divide both sides by that factor and multiply both sides by dt, then what I've got is the result would be di is equal to epsilon naught over r minus I is equal to r over L dt. And now I can do a u substitution. Okay, so let u equal to epsilon naught over r minus I, and then du, this term is constant, so the derivative is 0, so it would just be negative di. So then I would have, with this u substitution, I would have di is equal to negative du over u is equal to r over L dt, and no reason I can't transfer that negative sign over. Okay, and now this becomes a logarithm, so ln u is equal to negative r over L times t. Okay, and exponentiate, right? If I exponentiate, I'm going to get u is equal to e. Technically, okay, there's a constant out here, a integration constant. And so I really should write this down as that integration constant times e to the negative r over L times t. But u was equal to epsilon naught over r minus I, right? Epsilon naught over r minus I. And so one more thing we can do is look at this term, and if I write this as e to the negative t over a constant, let's call that constant tau, okay, because this is going to play the role of a time constant, then this is the same thing as e to the negative t over LR. Okay. So I'm dividing t by the fraction r, which actually gives me negative r over L times t. But I'm defining this time constant tau just like we had an RC constant of r times c. My time constant here is L over r. Okay? And then we also have negative I is equal to negative epsilon naught over r plus c over negative, let's write it in terms of our time constant, negative t over tau, and multiplying through by my negative sign, I is going to be equal to epsilon naught over r minus c e to the negative t over tau. Okay? And your book denotes the time constant with a subscript L to denote inductive time constant as opposed to capacitive time constant, right? But there's something that we still have yet to do, and that is evaluate the constant c. Okay? We have to evaluate the constant c. And to do that, okay, we have to make note of what's going to happen, right? We have to make note of what's going to happen. When I flip my switch to turn this kind of circuit on, right, the inductor is going to have some induced voltage opposing the current. Okay, opposing the battery, I should say, because its induced potential will be acting opposite the direction of the battery. So the induced potential, being a negative potential, is going to be acting this direction, right? And so what that means is that your current is not going to be immediately established. What that implies is your current will have a value of 0 at time equals 0. Okay? So our current will have a value of 0 at time equals 0. So this is our initial condition. So if this is the case, then we've got 0 is equal to epsilon naught over r minus c times e to the 0. And e to the 0 is 1. So epsilon naught over r minus c is equal to 0, or c is equal to epsilon naught over r. So my current as a function of time can be written like this. Okay, but I can factor out the epsilon naught over r. Okay, so this is the solution to my problem. And note what epsilon naught over r is. Epsilon naught over r would be the current due to Ohm's law if the inductor were not present, right? If the inductor were not present and negative L di dt were 0, then I would just have Ohm's law that says this. And my current would be epsilon naught over r. So epsilon naught over r represents the maximum current in the circuit. Once the effect of the inductor has died away, the maximum current will hold, and so this will just be the maximum current. you could label it I naught if you like. And then our current as a function of time is equal to is equal to I naught times the quantity 1 minus e to the negative t over tau. Now, what does this quantity look like? If I were to graph this, what this quantity looks like is like this. This is not an exponential decay curve, and this is not an exponential growth curve. Okay? This is not exponential decay, and this is not exponential growth. But what this implies is, again, this epsilon naught over r implies a maximum current I naught. There's a maximum current I naught that my current can reach. And if it starts at 0, what will happen is it will grow like this and then asymptotically approach that value. Okay? It will asymptotically approach that value. As time goes on, it will get closer and closer and closer. That is how the current will grow in an inductance circuit, in an RL circuit. Okay? Now, what about the potential across the inductor? Okay? What about the potential across the inductor? Well, if I look at the potential across the inductor, I've got this expression. And I know what the function of the current looks like. Okay, so I've got my current. If I take the derivative, derivative of 1 is 0, and so then this just becomes negative 1 over tau e to the negative t over tau. And so this becomes negative I naught over tau e to the negative t over tau. And when I multiply that by L and the negative sign, it becomes L I naught TL. If you really wanted to, you could write tau, this L over tau, right, is the same thing as L over R. So this is the same thing as R. Okay, so this would be the same thing as R I naught e to the negative t over tau, right? And R I naught would be the initial potential across, not the initial potential, I'm sorry, it is not the initial potential across the resistor. It is going to be the initial or the total potential across the battery, right? Because once the total current has been established in the resistor, that means the inductor's effect has completely died away, and this value via Ohm's law would equal epsilon naught. So the inductant, or the potential across the inductor rather, is equal to the potential across the battery times e to the negative t over TL. So this is an exponential decay curve. So whatever the initial potential across the battery is, what this is telling you is the initial potential across the battery, all of it is felt across the inductor at first. All of it is felt across the inductor at first. And as the current grows and the effect of the inductor dies away, the current is going to grow with that growth rate, and the potential across the inductor is going to decay away exponentially. And as a result, the potential across the resistor would do the same thing that the current does, and as the potential across the inductor exponentially decays, the current, or the potential across the resistor, is going to grow like this, because the potential across the resistor would be written as the potential of the battery minus the potential of the inductor. So you would get the exact same form mathematically as you do the current. Okay. So your potential across the resistor is going to grow just like your current is, and that should make sense because everything that happens with the current will happen with the resistor in step. Okay, so that should be no surprise. Now, before we are done here, let me make a quick note about the energy in an inductor. Ooh. And let's actually make that a little bit cleaner. Okay, so the energy in an inductor. First things first, I'm going to give you the result and then we will prove it. Okay, we're going to give you the result and then we'll prove it. So it shouldn't come as much of a surprise that the energy can be written as 1/2 times a constant times a variable squared. Okay, so this follows the form of kinetic energy, this follows the form of potential energy of a spring, and this follows the form of the electric energy, right? 1/2 CQ squared, okay? Or I'm sorry, 1/2 CV squared. And so we have this formula. Now, how can I show this? Okay, well, once again, let's start with the potential across an inductor, and I'm going to drop the negative sign because all I'm interested in is the magnitude for the moment. Okay, so this is the potential across the inductor, but remember that power is equal to I times potential, current times potential, or IV, or in this case, current times potential epsilon. Okay, but remember this is also equal to the time derivative of potential energy. So power is equal to the time derivative of potential energy. So what I'm going to do is say that power is equal to EI, which is equal to LI DI dt. Okay, so I'm just inserting an I into the expression for potential. And this is equal to du dt. Okay, so u, or du first, is going to be equal to we can cross out the dt's, and this is going to be equal to L I D I. Right? And u is then going to be the integral of L times I di. And if my current starts from some starting value 0, if it starts from 0 up to some whatever value it may be, let's call it I prime, okay, then this is going to be equal to, L can come out of the integral since it's constant, and the integral of I di would be 1/2 I squared evaluated from 0 to I prime, and this gives us 1/2 L I prime squared, where the prime is just noting that that is some specified maximum current. Okay, there's nothing peculiar about the I prime here. It is just a maximum value of current, and therefore the form matches the form stated at the beginning of the slide. Okay, so we have energy and inductor. We looked at the derivation for how current and potential across an inductor are a function of time. And in the next video, we will look at the oscillations in an LC circuit. What happens if I put a charged capacitor and an inductor together in a circuit without a power source? What happens? And we will see what occurs in that situation. So stick around.